So for the do now, this is actually really the only concepts from colligative properties that I'm going to be testing on. So I'll talk more about videos 14 and 15 and what you need to know and what is just kind of extra information that'll be useful for the future. So for number one, and really it's just the only do not question, what happens to the following when you add a solute to create a solution? So the three colligative properties that we're going to focus on are boiling point, freezing point, and vapor pressure. So when we're looking at colligative properties, I want you guys really just to know the conceptual idea of boiling point, freezing point, and vapor pressure. So whether it goes up or goes down when you create a solution and why. So if we think about boiling point, let's say I have a beaker and it has water in it. So I have a beaker that's water. And into the beaker of water, I add NaCl. So once I add NaCl into water, because NaCl is a soluble ionic substance, it's going to break apart into ions. So I'll have Na+, Cl-. So now in this container, I have Na+, Cl-, and H2O. Boiling point is actually one of the colligative properties that people, I don't want to say get confused on, but they just mix up because they just use what they know from like cooking, and they think that it applies to boiling point in a little bit different way. So when you actually add NaCl to H2O, so if this is on, let's say this is on a hot plate, water normally boils at 100 degrees Celsius. When you add a solute, whether it's NaCl, whether it's glucose, no matter what solute it is, if you add a solute, you now have to add more heat to not only move the water molecules, but to also move the solute particles as well. So when you add a solute, you increase the boiling point. That's why the colligative property is called boiling point elevation, because the boiling point of a solution is higher than the boiling point of the pure solvent. So a lot of times people think, well, I add salt to water when I'm cooking, and salt is really just added to water for taste. Because what it actually does is it causes the water to boil at a higher temperature. So the more salt you add, the higher the temperature is that water is boiling. So let's say maybe instead, once I add the NaCl, the solution boils at 110 degrees Celsius. So when you add a solute to create a solution, boiling point goes up. Why? Because now you have to not only heat the water, but you also have to speed up the solute particles as well. For freezing point, so if we think about freezing point, we're going to pretend that this is a sidewalk, and we have a patch of ice on the sidewalk, right? Ice is nothing more than water. Well, if we have a patch of ice, or let's say it's snowing, right, on the sidewalk, what do we lay on the sidewalks during the winter? Salt. Now, our salt is usually calcium chloride. Remember, the term salt just means you have an ionic substance. But we add salt to the sidewalks or to the roads. And the reason that we add salt to the sidewalks and to the roads is because once we add that solute, we've created a solution. And now, in order for this solution to freeze, it has to hit a lower temperature. So when we create a solution, the freezing point of the solution actually goes down, which is why the term for this colligative property is freezing point depression. Freezing point goes down. So that's why if it's the middle of the winter, right, and we have a lot of snow coming down and it's negative 10 degrees Fahrenheit, we still could see the roads freeze. And that's because if we still get to that freezing point, It's still below 0, but it could be -10, -15 degrees Fahrenheit. Now we're freezing the water and the solute. So freezing point of a solution goes down because now not only do you have to freeze the water, you have to slow the water molecules down enough to freeze, but you're also slowing down the solute particles as well. And then vapor pressure. So if we think about vapor pressure, if we come back up to this beaker, normally we have water. All right, let's assume there's no solute in here, it's just water. Water will have a certain pressure above the liquid. It has a certain vapor pressure. Well, if I add a solute, now it's harder for the water molecules to become gas. It's harder for the water molecules to escape the liquid phase and become gas. You're going to have less of gas up here. You're going to have a lower vapor pressure. So vapor pressure will go down. And again, the term for the colligative property is vapor pressure lowering. So you have boiling point elevation, freezing point depression, and vapor pressure lowering. This is what you need to know about colligative properties. So you just need to know the conceptual understanding and why boiling point goes up, freezing point goes down, and vapor pressure goes down, which is what we just looked at. Some other things with colligative properties. In video 14, question 1 was marked incorrectly. So colligative properties do not depend on the identity of the substance, only the amount. So I think that it was a true-false question. False was the correct answer. So colligative properties only depend on the amount of solutes that get added. The more solute that gets added, the more the colligative properties will be affected. And then I will not be asking you any questions related to osmotic pressure or to Raoult's law. I'll talk more about the math in a couple slides. But again, all that you are responsible for knowing for quizzes and for tests is this information right here. So the conceptual ideas behind colligative properties. Any questions on the do now? All right. So looking at this week, you can see everything like the lesson plans up here. Tonight you'll watch the last video. It's 5 minutes, and it's all conceptual. So it's looking at colloids, how they're different from solutions. We're going to finish up chapter 13. So we're actually, and really after today, because we'll look at some other review with multiple choice questions. But after today, we're done with the new stuff for chapter 13, which means we're done with the new stuff for for unit 4. Tonight's video will not be tested. I'll talk more about that on the next slide. Mastering is due Thursday. So Thursday at 2:30, I have all of the practice, so all the recordings from last week, which we went over number 23 together, and then I did a separate video on number 27. Everything's posted on the practice YouTube playlist, which is linked under the Unit 4 materials on Google Classroom. I switched one of them, I think it's 27 to bonus. So mastering is now 25 points with 5 points of bonus. And everything is broken up by video. Everything is still the same for mastering. The chapter 12 and 13 quiz is Wednesday. So for everyone, it's Wednesday. So you guys will be in class. So you'll take it in class. It's all multiple choice. So it's 20 multiple choice questions. You will be allowed a calculator, periodic table, equation sheet, everything like that. And then unit 4 test. So now that we're done with chapter 13, we're done with unit 4. Unit 4 is chapters 11, 12, and 13. So intermolecular forces, solids, and solutions is unit 4. So depending on the group, so what gold group takes it Monday, green, and then anyone that's completely online takes it Tuesday. So you guys will take it Tuesday. So that's next week. So then you'll see Thursday and Friday we'll be reviewing unit 4. So that's kind of looking at this week and then focusing more specifically on today. So today we are going to look at example 11 in the notes, which is page 14. This is looking at the math that's involved with colligative properties. So it's not tested on the AP exam. I'm not going to ask you questions for quizzes or tests. but it will be useful for future college classes. So like for college chem, it's still important that you've at least seen one type of these examples. So we are going to go through the example together. And it'll be useful because we're going to talk about the Van Hoff factor, which is what a lot of people had questions on from the video. Then we're going to look at mental math. So we're going to start looking at tips and tricks for solving problems without a calculator. Now, right now, I'm still, just like I said on the quiz, I'm still allowing you to use calculators. But the reason that we're going to start looking at this is because on the AP test for the multiple choice section, you do not get a calculator. So it's important that we start looking at practicing mental math. And then we're going to actually go through solutions, multiple choice questions. So these are practice AP questions related to solutions. So we're going to go through some of them together. And then I'll actually have you working in small groups for the rest of the questions. And then we'll actually go through the answers tomorrow as well. So just again, you will not be tested on the math from video 14 and anything from video 15. So this is just info that is going to be useful for college chem. So since this is also dual enrollment, there are some things that we still need to talk about even though it's not on the AP test. But you need to know conceptually how colligative properties are affected. So that's what you need to know for quizzes and tests for us. Okay, so what I want you guys to do kind of while we're like switching over. First, in the top tray is the mental math rules sheet that we're going to go over after the example. So you can grab that. And then also on the counter is the Unit 4 review packet. So some people like having that early so that they can start looking through it. So if you want to grab it now just so that you have it, you can. But grab those two things and then also make sure you have your notes out. So kind of do all that. If you need to grab things, you can. But then go ahead and get out your notes, calculator, and flip to page 14.
Outside, give it to him, and come back.
All right, so guys, at home, you can get out your notes, flip to page 14. All right. Okay. So for this first part of class, we're going to go through this example. Again, this is on page 14 of the notes. If you want to make yourself a note next to this and just say like not on the test, that's fine. I will not be asking you questions like this on the quiz or on the test. However, there are things that you will see in the future. So if you take a general chemistry class your freshman year of college, you will very well see questions like this regarding colligative properties. So I just want to make sure that you've at least been exposed to it a little bit. This used to be tested a lot on the AP exam, and then they shifted some stuff around. So now this is no longer on the AP test. All right, so again, this is page 14. This is example 11. So for this problem, it says a 0.562 gram sample of an unknown substance was dissolved in 17.4 grams of benzene. And so if it's dissolved in benzene, that means benzene is doing the dissolving, so that's the solvent. This unknown is getting dissolved, so it's the solute. So remember, the solute is what we have in the lesser amount. The solvent is what we have more of. The freezing point of the solution was 4.075 degrees Celsius. The freezing point of pure benzene is 5.455 degrees Celsius. So notice how the solution has a lower freezing point than the pure solvent. That's because we added a solute. And then for pure benzene, they give us two constants. So the freezing point constant, the boiling point constant. And it says assume that the solute is a non-electrolyte. So a non-electrolyte means that it does not dissociate. So a non-electrolyte means it doesn't dissociate. So that means it doesn't break apart. And the reason that that's useful is because that means that I is 1. So the Van Hoff factor is 1. So we'll talk more about the Van Hoff factor in like more specifics in part D. But for now, if it says it's a non-electrolyte, it doesn't dissociate, so I is 1. That means it remains as 1 particle. So for part A, what's the molality of the solution? Okay, well, I know from what we've looked at before that molality is moles of solute over kilograms of solvent. I know that from what we talked about last week. Well, if I try to figure this out, I don't know my moles of solute. And I can't figure out my moles of solute because I have the mass, but I don't know what it is. So I don't have the molar mass. So what I'm going to have to do is I'm going to have to solve for molality in a different way. And this is where having the freezing point information is useful. So if I have the freezing point information, I'm going to use the freezing point formula. So delta TF, that's the change in freezing point. Deltas change. So the change in freezing points is negative I times KF times M. So delta TF is negative I times KF times M. It's negative because freezing point goes down. I is the Van Hoff factor, K is a constant, M is molality. So now I can actually calculate molality based on freezing point. Now delta T is no different than what we looked at when we were looking at heat. Delta T is always final minus initial. So if I think about it over here off to the side, if it's final minus initial, final is the solution that we create. So it's going to be the temperature of the solution minus the temperature of the solvent. So this F stands for freezing, right? So the change in freezing points is the temperature of the solution minus the temperature of the solvent. So whether you want to do that separately or you want to do it all at once, it's up to you. I'm just going to put everything in at the same time. So the freezing point of the solution is 4.075. The freezing point of the pure solvent is 5.455. Negative I, we've said, is 1 because this is a non-electrolyte. It does not break apart. KF is a constant. So KF, 5.065. And M is molality. That's what we're solving for. So we can find the molality of a solution using freezing point information. So if my calculator, and so we have 4.075 minus 5.455. This is negative 1.38 equals negative 5.065 times molality. I divide by negative 5.065. Molality, 0.272. And remember, for your units for molality, you can either do the small m for molal, or you could do moles per kilogram. Either one would work. So all we did for freezing point is you can use the freezing point formula to either solve for a temperature or you could solve for molality. In this case, we were solving for molality. Now part B, so this is actually a very common use. So even in like a lab, there are a lot of chemists who actually use freezing point data to find the molar mass of a substance. So if we want to find the molar mass, so remember that molar mass is just grams per mole. So if I want the molar mass of the solute, I want the grams of the solute, and I want the moles of the solute. Molar mass is grams per mole. I can find the molar mass by taking the grams that were given in the problem divided by the moles, right, of that same substance. They gave me the grams right in the problem. They gave us the mass of this unknown that we were using. So 0.562 grams. I need to figure out how many moles of the solute did we have. So I need to determine how many moles of that solute did we have. Now remember, everything builds. So I can use something that I found in part A to help me answer part B. I found the molality in part A. Remember that molality is moles of solute over kilograms of solvent. So I can find moles of solute. It gave me the mass of solvent in grams. 1, 2, 3. There it is in kilograms. So it's 0.0174 kilograms of solvent. So all we're doing here to find the molar mass, we need to solve for moles. We use the molality to solve for moles. And this is something that we did last week. We had molality, we could solve for moles. Mastering has to do the same thing. So if I multiply 0.272 times 0.0174, I get 0.00474 moles of solute. So again, all I'm doing is I'm using the molality from part A. Kilograms of solvent was given in the problem, while grams was given. We just went to kilograms. So here's my moles of solute that we got in this problem. So grams of solute, that's what we used. Moles of solute we could calculate from molality. Grams over moles, that's our molar mass. So 0.562 divided by 0.00474 moles. We should get a molar mass of 118.5 grams per mole. So a lot of times, if a chemist is in a lab, they can do these freezing point depression experiments. And if they know that they've narrowed an unknown down to 3 substances, well, then they could use the molar mass and they could match that molar mass up to 3 substances and see whichever one is closest. So from freezing point data, we can find the molality, and from molality, we can find molar mass. Questions on A or B before we look at part C? Okay, so for part C, this is going to be similar to part A, except now we're going to be looking at boiling point. So just a quick review. Remember that normal. So notice how it says normal boiling point. If it says normal, that means it's at 1 atm. Right? That's from chapter 11. So normal boiling point means that's the boiling point at 1 atm. So the normal boiling point of pure benzene is 80.2 degrees Celsius. What is the boiling point of the solution? So in this problem, this is similar to freezing point. The equation is almost identical. One small difference. So if we're looking at boiling point, the change in boiling point, delta T B is change in boiling point, is I times KB times molality. There's no negative because boiling point goes up, so it needs to be a positive number. So delta T, again, is the same thing. Delta TB, if it's final minus initial, it's the solution minus the boiling point of the pure solvent. So I'm going to start, if I'm trying to find a boiling point of 1, either the solution or the solvent, I'm just going to solve for delta T first. Now, part C is building on everything so far. So if you look up in the information that they gave us, again, we knew that I was 1. We knew I was 1 because it said it was a non-electrolyte. KB was given to us in the problem. KB was 2.61 degrees Celsius per molal. And molality we already calculated. 0.272 moles per kilogram. So the change in boiling point is 1 times 2.61 times 0.272. So if we plug this into our calculator, 2.61 times 0.272 is 0.711 degrees Celsius. Now that is the change in boiling point. So that means from the solvent to the solution, the boiling point will change by 0.711 degrees Celsius. Now something to keep in mind, the boiling point increases. Remember colligative properties, it's boiling point elevation. So that means from the solvent to the solution, it should increase by 0.711. So 80.2 plus 0.711, so we can keep it some free sig figs, gives us 80.9 degrees Celsius. And you can also plug it in up here, right? 0.711 equals T of solution minus 80.2. You add it over, 80.9 degrees Celsius. Or we can just remember boiling point should go up. Boiling point should increase. So that's the math. Now I want to look at part D. And this is where a lot of the questions came in video 14. It asked about the Van Hoff factor. So we're going to talk about the Van Hoff factor, and then we're going to talk about probably the most important thing on this whole page, and something that's going to be useful for us moving forward. So this asks, what's the Van Hoff factor? Explain whether using it was necessary in this calculation. So if we write out what it is, so the Van Hoff factor represents the moles of ions that dissociate in the solvent. So the Van Hoff factor represents the moles of ions that dissociate in the solvent. So in this problem, I equals 1. Because the solute is a non-electrolyte. So we didn't have to worry about the Van Hoff factor in these calculations because I was 1. The solute was a non-electrolyte. That means it doesn't dissociate. So I can put it in parentheses. Non-electrolyte means does not dissociate. It means it stays together. So essentially, I is the number of particles that the solute breaks up into. I is the number of particles that the solute breaks up into. So in the notes, it was on page, 11. There was a little table that had sucrose, NaCl, K2SO4, and MgSO4. And it said what the expected value of I was. Sucrose has an I of 1. That's a molecule. It's a covalent compound. I is 1. NaCl, I was 2. K2SO4, I was 3. So it's how many particles it breaks up into. Now, here's maybe the most important thing that we're going to write down on this entire example. All right, so something that we need to remember from from chapter 4, which is part of summer work. Strong electrolytes completely dissociate. So strong electrolytes are the ones that completely dissociate. These are the ones that are going to have values other than 1. Now you look at this and you're like, well, I don't remember what strong electrolytes are. Well, strong electrolytes, there are 3 things that are strong electrolytes. One of them is soluble ionic compounds. Soluble meaning it dissolves in water. Remember, that's anything with potassium, nitrate, ammonium, and sodium. So if it has potassium, nitrate, ammonium, or sodium in it, it's ionic, it's going to dissolve in water. That's why K2SO4 breaks up into ions. It breaks up into 3 ions. If it's K2SO4, it breaks apart into 2 potassiums and 1 sulfate. So its I value is 3. The other strong electrolytes are strong acids. There are 7 strong acids and strong bases. So for example, I'm not going to list all 7 strong acids, but for example, HCl is a strong acid. It breaks apart into H plus and Cl minus. Another example, HNO3, strong acid, breaks up into H plus and NO3 minus. Right? Remember, there are 7 strong acids and then strong bases. So your strong bases are ionic, but remember that it makes the lowercase b on the periodic table. So lithium down in group 1, calcium down in group 2. You pair any of those metals with hydroxide. So like calcium hydroxide is CaOH2. That would break apart into 1 Ca2 plus and 2 OH minuses. So this is going to be the most important thing on this entire page. Strong electrolytes completely dissociate, and the strong electrolytes are soluble ionic compounds, strong acids, and strong bases. The reason that this is important is because when something dissociates, it becomes conductive. We'll talk about conductivity as I do now tomorrow. But in order for something to be conductive, it has to have ions flowing in solution. So if there's anything on this entire page that you remember, it's this part down here, dealing with strong electrolytes. Okay, any other questions from part C or D? All right, so if not, you are still going to need your notes out because that's where the multiple choice questions are. But before we get into the multiple choice questions, we are going to briefly talk about the mental math and the tips and tricks for doing math without a calculator. Now, again, as long as we have some people in class and some people at home, we're going to use calculators just because I can't ensure that everyone at home is not using a calculator. However, right now on the AP test, they've still told us everything is like normal. So that means multiple choice is no calculator. For your response, you get a calculator and everything else. So for the mental math, right, so this is the page that was in the top tray. So these are just some rules and some tips to help with doing math without a calculator. And it's tough because I know that we're used to using calculators, and there are times that I have to kind of like take a step back and think about how I would do it without a calculator. So I've starred some of them, and you have them starred on your page as well, because some are going to be more useful to us right now than others. So the first thing to remember is that when you're multiplying, right? So when you're multiplying, reduce when you can. And so when it talks about it being commutative and associative, that means you can move the numbers around if you need to. So like 4 times 21 is the same as 21 times 4. And the reason that you can do that is because notice I can reduce 21 and 7. 21 divided by 7 is 3. I can reduce 4 divided by 2. 4 divided by 2 is 2. So if I just saw this, I'd be like, yeah, I can't do that without a calculator. Remember that you can reduce down, make it easier. Another thing that's going to be extremely important is rounding. Round your numbers. For example, there are times when you're doing the ideal gas law. I can't do math with 0.08206, but I can round 0.08206 to 0.1, and that would be more useful. Once we start getting into more of the scientific notation, just remembering some rules with scientific notation. So if you have x to the a times x to the b, you can add those exponents. If you're dividing two numbers that are in scientific notation, right? If you're dividing two numbers, you can subtract your exponents. And then if you have, a number to the power and then another exponent outside of the parentheses, you can just multiply those. So those are some to help. There are other ones down here, but we haven't done logarithms yet or natural logs, so we're not going to worry about those yet. We'll be coming back to these later as well. So on the back of the page, right, round when you can. So instead of doing Avogadro's number times 4.1, round 6.022 to just 6. Because then you have 6 times 4, so you have 24 times 10 to the 23rd, instead of trying to do the exact math. We're going to look at some of this today. If you have decimals, put them in scientific notation. It's a lot easier to work with scientific notation than trying to do even 0.06 divided by 0.002. Can't do that in my head. But if I put it into scientific notation, it's a little bit easier to work with. And then again, when you're multiplying and dividing, try to reduce where you can. So this is just some helpful hints with mental math. What we're going to do is we're going to actually look at some practice AP multiple choice questions, and we're going to try them without calculators. So this is on, I think that's at page 16. Yeah. So page 16 of the notes packet. Now at the very end of the notes packet, so on the very last page of the notes, you're going to notice that you have an answer key. I gave you the answer key to the multiple choice questions. Now, not all of them are explained. So as you guys are working today, I will actually give you like my answer key as well. So it's actually like everything that the work that I did as well. So we're going to try 4 of them together, and then I'm going to have you work in small groups. And I'm going to show you on the first 4. Again, these are practice AP questions. I pulled these from old AP tests. So you'll see exactly the types of questions that they ask you. So for number 1, we'll at least get number 1 set up before the bell rings. So for number 1, a 0.2 mole sample of MgCl2. Okay, so I'm just going to underline this. 0.2 mole sample of MgCl2 and a 0.1 mole sample of KCl are dissolved in water and diluted to 500 milliliters. What is the concentration of Cl- in the solution? So on the AP test, when it's asking for concentration, it's more than likely asking for molarity. Now you can tell by the answer choices, capital M is molarity. So that tells us we're going to be calculating molarity. Now, we want molarity of Cl minus in the solution. So remember, molarity is moles over liters. So that means I want the total number of moles of Cl minus over the volume of solution. So for number 1, so again, if we want concentration of Cl minus, AP likes to ask questions like this where they're asking you about a specific ion. So for molarity, we need the total number of moles of Cl minus divided by the volume of solution. Remember, volume has to be in liters. So to find the total number of moles of Cl minus, we need to figure out how many moles of Cl minus are coming from NgCl2 and how many moles of Cl minus are coming from KCl. So I'm going to say, all right, I have 0.2 moles of NgCl2. So for every 1 NgCl2, how many Cl's do we have? Should have 2. All right, so 2 moles of Cl minus. So for every 1 MgCl2, we have 2 moles of Cl minus. So 0.2 times 2 is 0.4 moles of Cl minus. That's coming from MgCl2. So there's part of my moles. Now I need to figure out how many moles are coming from KCl. So if I come down here, 0.1 mole KCl. For every 1 mole of KCl, I have just 1 Cl minus. So that's 1-to-1. So that's going to be 0.1 moles of Cl minus. So I have 0.4 moles of Cl minus coming from NgCl2. I have 0.1 moles of Cl minus coming from KCl. So my total number of moles needs to be divided by the volume in liters. Right? Molarity is moles per liter. 500 milliliters, 0.5 liters. So again, without a calculator, 0.4 plus 0.1 is 0.5. Divided by 0.5 liters. What's 0.5 divided by 0.5? You say it's 1. So number 1 is D. So again, this is when we're looking for the concentration of a specific ion. So you have to figure out where is that ion, where's the amount of that ion coming from? So if we look at number 2, if 200 milliliters, so 200 milliliters of 0.6 molar MgCl2 is added, to 400 milliliters of distilled water. What is the concentration of Mg2 plus in the resulting solution? And I said assume volumes are additive. So before we even worry about what math we're doing, I want us to just look really quick. So we have MgCl2. We have a sample of MgCl2 being added to distilled water. When you are adding something to distilled water, you are diluting it. This is a dilution problem. When you add something to distilled water, you are diluting it. The dilution formula is one of the most important formulas that is not on the equation sheet. The dilution formula is M1V1 equals M2V2. So you have molarity and volume of one substance equals molarity and volume of the same substance, just different concentrations. So 200 milliliters and 0.6 molar MgCl2 goes together. So I'll just make that my ones. So 0.6 molar, as long as your volumes are the same unit, you don't have to convert. So I have 200 milliliters of 0.6 molar. I'm trying to find the new concentration at a new volume. Now I underlined I double underlined the two most important words here. It's added to. So 200 milliliters is added to 400 milliliters. So the new volume is 600 milliliters. And in the problem, it even said, assume the volumes are additive. That means you're adding them up. Now you look at this initially and you're like, oh man, we still don't get a calculator. But if I divide both sides by 600, divide both sides by 600, reduce where you can. I can reduce 200 and 600 pretty easily because 200 over 600 is 1 over 3, right? 200 goes into 600 3 times. So now if I look at what I have here, I have 0.6 times 1, which is 0.6, divided by 3. 0.6 divided by 3 is 0.2. 0.6 divided by 3 is 0.2. Now, just really quick, this is 0.2 molar of MgCl2. We just want to double check. For every 1 MgCl2, there's 1 Mg. So the molarity of MgCl2 is the same as that of Mg2+. So 2 is A. So it's important when you're doing questions like this that you're reading it carefully. If it says it's added to, I would underline, I would circle something because that means you're probably adding the volumes together. Okay, then number 3, 360 milligram sample. 360 milligram sample of aspirin, and they give you the molar mass. Typically, they'll give you the molar masses in multiple choice questions. Is dissolved in enough water to produce 200 milliliters of solution. What's the molarity of aspirin in a 50 milliliter sample of this solution? So I know molarity is moles over liters. Now I notice here that I'm given 2 volumes. This 50 milliliter sample does not matter. What matters is how much aspirin we are adding and how much solution we are forming. This 50 milliliters would be no different than if I had a volumetric flask of hydrochloric acid in the fuel hood, and I said it was 6 molar HCl. And for a lab, you only needed 50 milliliters of it. I said, go back and get 50 milliliters of that 6 molar HCl. You took a beaker back, you got 50 milliliters. That sample is still 6 molar. It's just a smaller sample. So this 50 milliliters doesn't actually even matter. So what we need to do is we need to figure out how many moles of aspirin do we have and what's the total volume of solution. Now, notice that it's 360 milligrams. There's just like milliliters, there's 1,000 milli in one base unit. So 1, 2, 3, there's 0.360 grams in this sample. Now I need to go to moles, and they gave me the molar mass. So here's where you kind of do it one of 2 ways. You could put them in scientific notation, or what I like to do is I will just actually ignore this decimal just for the time being. What's 360 divided by 180? 2. Right? 360 divided by 180 is 2. But I have this decimal, so instead of 360, move the decimal 1, 2, 3 times. 1, 2, 3 times. It's 0.002 moles of aspirin. So 0.002 moles of aspirin, 200 milliliters is 0.2 liters. Now here's where I want to show you how putting things in scientific notation can be useful. Just reviewing scientific notation. If I want to put 0.002 in scientific notation, I'm going to move the decimal 3 times. It's 2 times 10 to the negative third moles. Because the negative exponent means it's a small number. 1, 2 times 10 to the negative first liters. So I can solve it this way now. 2 divided by 2 is 1. Then with your exponents, when you're dividing, you subtract. -3 minus -1 is -2. 1 times 10 to the negative second molar. 1 times 10 to the negative second is D. So 3 is D. Now here's another way you could do this. Some people say, well, if I look at this and I realize 2 divided by 2 is 1, so my answer is going to have it's going to be something with 1. 0.01, 0.1. The only one with a 1 in it is D. So that's another way that you could solve. But if there was one that was 0.1, one that was 0.01, you'd need to know how to do it, and you could use scientific notation. Now again, for us, for the foreseeable future, we'll have a calculator, but you very well could do a question like this on the AP test. Any questions before we look at 4? 4 is the last one we're going to look at together. All right, so number 4. And you're going to notice that, again, we have 2 amounts. So for number 4, a 40 milliliter sample, 0.25 molar KOH is added to. So I suggest right off the bat, underline, circle, double underline, added to. Right? Because added to means that you have to add your volumes together. So I'm going to look at 40 milliliter sample is added to 60 milliliters of 0.15 molar barium hydroxide. So I'm trying to keep everything together. What is the molar concentration of OH minus in the resulting solution? So molarity means I want total moles of OH minus divided by liters of solution. So for some people, they like finding the liters of solution first. Added to, and it even says assume the volumes are additive. 40 milliliters plus 60 milliliters. 40 plus 60 is 100 milliliters. Now it needs to be in liters to go on the bottom. So 0.1 liters. Now we need to figure out the total moles of OH minus. So I'm going to look at KOH and BaOH2 separately. So I'm going to start by looking at KOH. So 0.25 molar is X moles, 0.04 liters. 1, 2, 3. 0.04 liters. So if I solve for X, I get 0.25 times 0.04. Okay, so there's 2 ways you can solve this. You can put them in scientific notation and you can solve. Or sometimes if you're just multiplying, I like to just use the decimal. I like to just move the decimal. So if I move my decimal for 4, I move it twice. What is 0.25 times 4? We have 0.25, 0.25, 0.25, 0.25. 4 quarters in $1. 0.25 times 4 is 1. So let me move my decimal back. 1, 2. We get 0.01 moles KOH. Again, I just moved my decimal. You could do scientific notation. You could do 2.5 times 10 to the negative first times 4 times 10 to the negative second. 2.5 times 4 is 10. Negative 1 plus negative 2 is negative 3. Maybe 10 to the negative third, and you can put it back in standard. So here's my KOH. Now remember, I want OH minus. What's my ratio of KOH to OH minus? For every 1 KOH, I have 1 OH minus. That means I have 0.01 moles of OH minus. That's coming from KOH. Now let's look at barium hydroxide. A little dotted line here. 0.15 X moles of barium hydroxide over 0.06 liters. Oh, man. So if I multiply 0.15 times 0.06. Again, you could either do scientific notation. I like just moving the decimal when I'm multiplying. So I'm going to move the decimal for the 0.06. I'm going to move it twice for now. So I can do 0.15 times 6. I think a thing's really weird. I think about this and I say, okay, if I do 0.15 times 2, that's 0.3. If I do that 3 times, it's 0.9. However you can solve it. All right, so 0.15 times 6. Essentially, you're adding 0.15 together 6 times. Here's 0.3, 0.3, 0.3. That's 0.9. I need to move my decimal to get back to 0.06. Again, if it's easier for you to say, I just want to do this over once, 1.5 times 10 to the negative first times 6 times 10 to the negative second. You do that as well. 1.5 times 6 is 9. This you get 9 times 10 to the negative third. Multiply these numbers, add your exponents. We get the same thing. This is a barium hydroxide. .009 moles of barium hydroxide. We have twice as many OH minuses. So 0.009 times 2 is 0.018. Again, because there's twice as much OH, you're going to have 2 times as many moles of OH minus. So if I look at this, I have 0.01 plus 0.018 divided by 0.1 liters. So I notice that I have 0.028 divided by 0.1. Yeah, I'm going to see a 2 and an 8 somehow. 0.028, it's not going to be 0.028 because it's divided by 0.1. 0.28, 2.8, right, something like that. Look for that answer. Look for one that looks like that. So for 4, it's C. Now this one is very involved. You would probably see out of 60 multiple choice questions, maybe 1 or 2 like this. Most of them are going to be like 1, 2, and 3, right? Where it's a little bit easier to work with. So I'm going to actually have you guys do like 5 through the end with small groups. But here's a little hint I want to give you for number 5. Notice in these answer choices, A and B are similar and C and D are similar. The only difference between them are significant figures. So when you're looking at number 5, it's asking you for molarity. Remember that molarity is moles over liters. So I'm dividing. When you're dividing, you're looking for your least number of sig figs. You look at this given information. Your grams and your milliliters are in 4 significant figures. Your answer should be in 4 significant figures because that's the least number. So I can eliminate B and D right away. So when you're working through this problem, you do not need to find an exact answer. You just need to find, is your answer going to be closer to 12 or closer to 1? Because you've eliminated based on sig figs.